Hey robot makers, hope you're having a good day so far. So do you want to know how to detect faces with your Trilobot or any Raspberry Pi robot with a camera module using OpenCV? Then this is the show for you, and it couldn't be easier to do. It's easier than you think. So let's dive straight in. My name is Kevin. Come with me as we build robots, bring them to life with code, and have a whole load of fun along the way. Let's go over to our keynote. So yes, today is all about face detection. So I've got my little Trilobot on the desk. It's running some Python code. It's very, very easy for you to follow along with this as well. So the goals of the session today are to create our companion robot. Companion robots react to people. That's one of the definitions of companion robots. So it's going to detect faces. It's going to change the lights underneath based on what faces it detects, as in, can it see one or not? Can it see more than one? And we're going to show you how to set up your Raspberry Pi. This is running a Raspberry Pi 4. How to install OpenCV and the Pi camera module, which you need for this. And then we'll have a bit of a demo. Okay, so setting up the Raspberry Pi is pretty straightforward. So I've been using Raspberry Pi Bullseye, the latest release, but it does need a few tweaks before you get started. So the first thing you need to do, and this is just good practice anyway, is do sudo apt update, and that will grab the latest patches from the repository, and then we do sudo apt upgrade -y to install all the latest versions of everything. So once you've done that, if you flash, I think this is correct. It might have changed last week because I think there was an even newer version of the Raspberry Pi OS released. But if you can't see the legacy camera option available, then you probably just need to do those two steps. Once you've done, then when you go into Raspberry config, and we can have a demo of that if anybody has any questions about that, you go to the interface options and then you go to legacy camera and you enable that. And what that does is Bullseye came with a brand new libcamera module for Python and for other Linux cameras, and they changed how it works behind the scenes. So it broke loads of code libraries, things like OpenCV. So to get that back working again temporarily while they get libcamera working, we need to enable the legacy camera, and that's called Pi camera. So that will allow us to use the Pi camera module, and we'll need to install that as well. So how do we install all these different bits and pieces? So OpenCV, I've tried this very different ways to get it installed on a Raspberry Pi. You can use pip install opencv-python. When I tried that on the build I have, it didn't work. It took a very long time, like maybe an hour, and then it came up with loads of error messages. The easiest way is just do sudo apt install python3-opencv, and you'll get a working copy of OpenCV in seconds. The next thing is you need to install Pi camera, which is, it should come enabled when you enable your Raspberry Pi camera, but just in case, sudo pip install Pi camera, and that will install it sort of system-wide on your Raspberry Pi. So that's how we get those two modules installed. So let's have a look at OpenCV and what we can do with that. So this is Open Computer Vision. It's a library that enables us to do some really cool things very, very easily in Python. And other languages too, but this is what we're going to be looking at today. So what we're going to be doing today is getting Pi camera to take a picture. OpenCV is then going to detect how many faces there are in that picture. It could be 0, 1 or more. We're then going to change the lights on our Trilobot underneath based on what it can see. So if it can see 0, 1 or more faces. And then optionally, we could write out a file with a bounding box around the face to show you which faces it has detected, so we can have a play with that too. So how does OpenCV work? We've actually looked at building our own models previously with things like the Jetson Nano. We built up our own training data set. We ran it through the TensorFlow to build out a model for us. But you can just download pre-configured models, and that's what we're going to be looking at today. So this uses something called OpenCV HAAR Cascade models, and that sounds very technical and very unfamiliar if you've not seen this before. So what is HAAR? HAAR is a mathematical sequence of rescale square-shaped functions that form a wavelet family. So if you don't know what that means, don't worry, we're going to look at that today. And just in case you don't know what HAAR is, it's from Alfred HAAR, who was a mathematician, and you can see there in the sort of late 1900s, early 20th century. And he did a lot around this type of thing with squares and so on. So what we want to do is be able to use one of these pre-existing models. So when we go into the OpenCV folder, when we've downloaded that from GitHub, you'll see that there are example folders in there, and inside there are some of these HAAR Cascade models. And they're just an XML file, they're not very large, and then you basically just use one that you want to, that's applicable to your particular use case. So on here, we're going to be looking at this HAAR Cascade frontal face default, and it's just an XML file. I think it's about 20 meg in size, something like that, so it's not very massive. So that's what we're going to be using. How does it actually work? So there is a number of features that could be detected with a HAAR Cascade model, and we are going to use the pre-configured model to detect things such as faces. So there's my face picture I took earlier, and it's going to do things like detect the eyes, the nose, maybe the shape of the head compared to the background, and then it's going to draw that bounding box around it and say that it's detected a face. And if the picture's got more than one face in it, it will detect all of the faces. So the way that it does this is using these things called features, and they essentially just black and white rectangular shapes. And we can do some really crude things with those, and surprisingly it works very fast and very efficiently. So the first block that we've got there can detect edges, it can detect lines going down. So we look at our face, you know, it might detect that there's a nose sort of shape. The other things like line features, where you've got a line going across. Eyebrows and the ridge of your eyes are darker than the rest of your face, so that will be useful, that particular one there, for detecting that kind of configuration. The bridge of your nose might be useful to detect using this line feature. And then there is one that's called the 4 rectangles, and it can rotate these round as well to see if there's something significant with that. So features is what we're actually going to be detecting using this HAAR Cascade. So you can see their eyes are darker than the rest of the face. The bridge of the nose is lighter than the area than the eyes. So they're all called features, and that's what this algorithm is going to detect. So if you like what I do and you want to see more of this kind of thing, you can always go over to buymeacoffee.com/Kevin McAleer, help support the show. So either buy a coffee, or you can go to the YouTube membership, just click the join button. I think it's about $3 a month, something like that. And that can help just keep the show going along. So let's have a look at a bit more of a deeper dive at how these HAAR features detect faces and other structures. So let's have a look at some examples of this. So feature detection works by adding up the values of pixels underneath the dark area, the black area, and comparing them with the sum of the pixels under the white area. So it's very black and white, very binary. Without optimization, we'd have to scan the entire image pixel by pixel and looking at every single feature at every scale possible. So just think about how that would work. That would be super inefficient to do that. So for a 24 by 24 pixel grid, that would mean there are 180,000 possible features to test for, and that's basically just testing for one of these features, and that we could be testing for quite a few that make up a face, for example. So the word cascade is to do with how that it detects features. So it will look at the first feature. So say it's trying to find eyebrows in an image. Once it's found that there is an eyebrow area, and that's returned like a positive value, we might then go on to say, well, try and find the bridge of the nose within that same area, because that means that it's likely to be a face. If it doesn't find the eyebrows, then we're not going to bother looking for anything else either. So we've got a bit of an efficiency there. The cascade is the different layers that it goes through, the different feature sets. So it doesn't waste time looking for features if it doesn't find the first one in the set. So there's a thing called an let's get this right, an integral image. So an integral image is an array whose values are the sums of all the values in an image. So if our original image was an 8 by 10, this should be a pixel, each with a value between 0 and 255. So when we take a picture, what we normally do with machine learning is make that grayscale. We don't normally look for colours in it when we're doing detection of objects. We just try and do it in black and white because it's a lot easier to deal with. There's basically just one plane of things we're looking for. And each pixel can have a value between 0 and 255, so one byte's worth of data. So what we've got here is an image, but just displayed using those raw numeric values. So that's what it would look like as a very scaled down. It's very common that you would do that as well in open vision. In computer vision, you would normally scale down a very large image to be something very, very small, because you don't need that that high definition. You just need something that's quite simple to deal with. So then integral image is the sum of pixels in a given area. So we're going to walk through this example. Bear with me, it makes sense. So the algorithm begins to populate the integral image, which is like a separate image to our regular image, by calculating the sums of the values in the original image following a specific pattern. And it's easier if we look through this as an example. So what the integral image does is it has cells, and they're not necessarily pixels. And this is one of the ways we get the efficiency. It's the sum of all the values in the corresponding area on the original image. So this could actually be, 4,000 by 4,000, for example, and that area might just make up 100 pixels by 100 pixels. So it's a way of sort of scaling things out. And this is what HAAR did with his wavelets. Okay, so we're going to calculate. We're going to go to the original image, we're going to look at all the values of the pixels that we just had in that array, and then we're going to sum them up. And we're going to draw a line from the bottom left edge, the bottom right edge going straight up, and from the bottom right edge going to the left. So let's have a look what that looks like. So here's our original image. There's all the pixel values that we have in grayscale, and we're going to just add up all the different values that are in that area there. So once we've added those values up, we're going to put the sum of them in the same square on our integral image. So in this case, it was 51. If you don't believe me, you can go back in the video and you can count them up and you can see that it's 51. I checked just to make sure. So we're going to put that in our integral image. So we're going to leave that as our sort of purple, bluish sort of square. We're going to try another one. So let's try this value here. So we're going to add up all the different values that are in this original image, and then we're going to put it in the same square but on our integral image. So that's going to be, I think it's 80 on this one. And then we're going to fill that into our integral image. And you can notice a pattern that's going on. So a cell in an integral image corresponds to a specific area in the original image. And the value of that cell is the sum of all the corresponding pixels in that area. So in that sort of rectangular area going from the very bottom right edge to the top left. So that's going to allow us to do some very quick maths in a second. So we can now fill the rest of our integral image up. So you can see there the values get higher and higher the further to the bottom right we go, and lower to the top left that we go, because that's how we're doing the math on this. And what this means we can do is we can say here's an area on our original image and we want to detect a feature in there. And what we want to do with our HAAR Cascade model is basically just get one of those features and then say, is this area higher or lower in value? So do the pixels add up in one side of that feature, so say the black side, are they lower in value than the cells in the white area? So once we've got this integral image built up, we can do that kind of math very quickly because we just need to look at one value. We don't need to do that math, we've done it once already. So let's just read what it says here. Let's select an area in the middle of our original image and find the sum of all the pixels that are in there. So we've already done the math, we don't need to actually add anything up extra here. So this is only 5 by 3 pixels, but it could be as large. So we could just add up the numbers, all the 15 numbers up. But if this was like 100 by 100 pixels or 1,000 by 1,000 or ad infinitum, that'd be a lot of numbers to add up. And that's where the integral image shines, because we've already done that math already. We've pre-calculated this. So each cell of the integral image corresponds to the area on the original image, and we can find the sum of that area that holds the value that we have outlined. So what we essentially need to do to find the sum of all these things here is we need to look in this value down here at the bottom right, but then subtract off the top section. So there's going to be a section up here that we need to erase, and there's also going to be a section down there that we need to erase. And we just need to make sure we don't double count this top area twice. And if we do that, we've only got 4 numbers to calculate, and we can do that very rapidly once we've done that initial calculation. So the first thing is to find the corresponding bottom right pixel in that red box that we just selected. So it's 215 in our integral image. This still includes the values outside of that red box, so we just need to make sure we remove them. So what we mean by is this is a whole block of images, so a whole block of pixel values here, and a whole block of pixel values here that we just need to take off that. So let's see how we do that. So the first one, we can take off that top row, and we look at the value there, it's 80. So we simply just take 80 from our 215. That's really simple math for us to do. That's 135. We now need to remove that column to the left, which is here, of the red box. to find out what else we need to take from that. So if you like these videos that I do, make sure you give it a like, a thumbs up, comment on the video as well, and that will give the algorithm a bit of stuff to tell it that it likes this kind of video. Right, so we're going to find the area of this little purple area at the top left here, and we want to make sure we don't double count this, because we've got two areas at the top of our rectangle. It's going to be double counting, so we just need to make sure that we add that 20 back in, because we've subtracted off that 80. We need to add that value back in there. So it's very simple for us to do that, because this area overlaps the original orange area that we've already removed. So let's add this purple sum to our working sum, 135. We're going to add that to 20 on there, so 155. Very, very simple maths, very, very fast maths for our computer to do. And then the final thing is this green area. So the sum of the left area marked in green is 72. We just look at that bottom right value again. And that means that we can subtract that from our working total, which is 175, and we get the value of 83. So that tells us the value of all them pixels in that block there is 83. And that means that we can then do that comparison with the other part of the feature that we're looking for to see, is it higher or lower, and therefore does that feature exist in the area that we're looking for. So that's how these HAAR cascades work. So what does it all mean? No matter how many pixels are selected in the original frame, we only need 4 numbers to calculate the sum of those values, and that means we can then detect whether that feature is present in the image area that we've selected. So 4 numbers is a lot easier to calculate than 180,000 different values that we need to calculate. So the process dramatically reduces the amount of calculation that we need to do. So I read a really good article on this from Ben Mouse. If you want to follow that, you can just click on that, not click on the link, you can go to levelup.getconnected.com, and then that particular article there, the integrated image, and it's got a whole bunch of characters after that, but I'm sure you'll be able to write that down. I'll put a link to that in the video description. Just a reminder as well that we go live every single Sunday at 7 o'clock Greenwich Mean Time. So if you want to watch more of these kind of videos, interact live on the channel, you can do. And I'll look forward to catching you on those. If you also want to join me on Discord, we've got our very own Discord server. So you can go to action.smarsfan.com/join-discord. Alex has just dropped a link in the chat earlier to that Discord link, so you can join us in there as well and continue the conversation at a deeper level. Okay, let's have a demo. That's quite a bit of heavy theory going on there, so let's get over and do some fun stuff. So I'm just going to get myself set up over here. So I have a Raspberry Pi. Let me just stop the code for a second, and then I can show you what we're doing. Okay, let's get myself set up over here. Right, so if I go over to here, maybe that one, that's good. Right, so I have over here a Raspberry Pi. This is the actual Trilobot, which is just sat on my desk over here, so you can see my Trilobot's just here. And, oops, that's the better view, isn't it? And I've just opened up a command prompt. So what I've done is I've downloaded the code for this. If you want to play along, if we just open up a window, I'll show you how to do this. So let's just zoom in a little bit so you can see what's going on. So we're going to do git clone https github.com/Kevin McAleer/companion_bot, and if you do that, it's just gone off the edge of the screen there, companion bot. So if I press return, it'll download that code. I think I've already downloaded this, so there we go. It's downloaded the code, and then inside there we've already run the apt-get update, apt-get upgrade. We've installed OpenCV doing the sudo apt install python 3-OpenCV, and we've also installed the Pi camera module using sudo apt install, let's just do it, Pi camera as well. I should say it's already installed there. Is it called Pi camera, Python camera? Oh no, it's not apt, I think it's pip on that particular one, because that's a Python module, I think. It's whatever I said in the slides earlier on. So I'll just try that. I think it's already got that installed, so yeah, requirement is already satisfied. Okay, so if we go into our Python, what's the best way to do this? Let's do it using Visual Studio. So on this Raspberry Pi, I've gone into the recommended software and I've installed Visual Studio Code. It's a really nice interface to work, whether it's on a Windows, PC, Linux machine like this, or a Mac. So I've just got a question there from Adam about pip, not pip3. Because I have the latest version of Python installed on here, because it's running Bullseye, Python 2 is no longer installed. So if we go to Python -- version, you'll see that it says Python 3.9.2, which is whatever. That must come with Bullseye, and therefore we haven't got Python 2 installed anymore. So when we do pip, it's by default pip3. Okay, so I have the code installed. Let me get to the right folder. I actually developed this as part of SmarsFan a long time ago. So let me just change the folder into our companion bot. And let's open that up. And you can see in this companion bot, when I zoom in a little bit for you, that we have, yes, it's trusted author. I trust myself for this. Let's just do Control-Shift. Okay. So you can see I've got a couple of files in here, and this is how simple it is. We have the HAAR Cascade frontal face default.xml. We open that up, you can just see it's just got a whole bunch of, let's just move that back a bit there, whole bunch of values in there. We don't need to worry about what they are. That's just the data that makes up the model. And then we've got our code. So let's have a look at the code, shall we? Let's just close that little window there, and we can scroll through this. So the first thing we do is we're importing IO because we're going to be working with files. The XML file that we just looked at, we need to use that, and the IO library helps us do that. We're going to be using the Pi camera module. That allows us to take pictures with our Raspberry Pi camera. We're going to be using the CV2, which is the OpenCV library. We're going to be using NumPy. NumPy is like a numerical Python library. You can do lots of image manipulation in that, like converting things to grayscale. That's what we're going to be using it for in here. We don't use time. I think we can actually comment that out because that's not actually used. So let's just do that. And because this is on a Trilobot, a Pimoroni Trilobot, and I've also got that library installed just by doing pip install Trilobot, we can pull all the different parts of that library in there too. We use that to change the colors. So the first thing we do is we create a little T-bot. That's our robot. That's how we're going to refer to it in our code, and that comes from the Trilobot class that's there. We had a look at that very briefly last week when we reviewed the Trilobot. And I've just got a piece of code here, this function called green light, and it's going to make the lights underneath our robot turn green. So T-bot fill underlighting, so we're making it black to begin with. So 0, 0, 0 just means the RGB values are going to be 0 or off. We're then going to set the underlight value for each of the different LEDs. So we've got light front left, middle left, rear left, front right, middle right, and rear right. And for the green light, so red, green, and blue values, we're just going to set the green values to 100%, so 255, and everything else to 0. And then the last thing we're going to do is say show underlighting, and that's going to actually make the lights switch on. So that's our green light. We have another one which is blue light, and all that happens on that one, it's exactly the same. I could just have one function really that's a bit more efficient, and you just pass in the RGB values. That probably stored in a constant, something like that, but just because I was quickly putting this together, I didn't bother with that optimization. So red, green, and blue. So this is the blue value there at 255. So that's our blue light. Same thing, it's going to fill the underlights to nothing, set all the lights, and then show them. And then this is the piece of code that does all the work. So detect faces, let's get this up. So the first thing we're going to do is we're going to create a stream. So there's a couple of ways that we can take pictures with our camera. We can either use a stream, which means keep taking pictures, or we can say save it to a file. So on this one, we're going to use a stream just because we don't need to actually save it out unless we want to. So we say stream equals io.bytes.io, and bytes.io is an array of bytes. That's all that is. It just saves a particular area of memory. And then we say with Pi camera as camera. That auto help things really not getting in the way there. So then camera.resolution is 320 by 240, so really low resolution. CGA, if you remember that back in the day. And then we're going to say camera.capture using the stream bytes.io, so it's going to fill the stream bytes.io with the contents of what's in the camera. And then the format that we're going to save that in is JPEG, so we're just going to refer to that in memory as a JPEG image. So then we're going to create an image buffer. using NumPy, and this means that we can do these manipulations like the grayscale, because when we take the picture, it'll be a full color picture, and for what we do with it, we don't need that color. So we create a buffer, we use NumPy, and then we say from buffer. That is really getting in the way, isn't it? That, let's just leave that down there. So I'll refer to it underneath. So from buffer, from the stream, get value, and then we say the D type is NumPy, and then it's an unsigned integer 8-bit. So just a value between 0 and 255, that means. The next thing we do is we say we're going to create an image variable, and that's going to use the OpenCV library, and it's going to do an image decode using that buffer that we've just created, and we're just going to pass in a 1 there as well. Not sure what that 1 means, but I'm sure we could just hover over that and it will tell us. The one time we want it to actually tell us some help, it doesn't do that, so that's particularly helpful. And the next thing we're going to do is we're going to import that Cascade file. So the face Cascade equals CV2, which is our OpenCV library, Cascade classifier, and then we pass in the name of the file. If I just scroll to the right there, we can see HAAR Cascade full frontal default.xml. So it's going to open up that XML file, and then it's going to have that classifier ready. We then need to convert the image to grayscale, so we create a little variable called gray. We use our OpenCV convert color, we pass in the image, and then we say cv.color grayscale, and we're using that blue, green, red to grey constant, and that means it will convert it from a blue, green, red image to a black and white grayscale. Grayscale, not black and white. Then this is the bit that actually detects the faces, and it's just one line of code. So faces equals face cascade, which is what we created up there using our classifier, detect multi-scale, and we say grey, which is the name of our new grayscale image, 1.1, which is, does it tell us what that means? And then 5. I think these are kind of like little knobs you can twiddle to say how big an image and so on, an area you want to search for. So before, when we were looking at the size of the area, remember the area doesn't necessarily map one-to-one with a pixel, it can be a number of pixels. That 1.1 and 5 will be to do with the granularity of that, and therefore how fast. So if we change that number to be a larger or smaller number, I bet it gets the algorithm to be faster or slower. Okay, so then we say print found plus the length of the faces, which is what we get back there. So this will be an array of the areas that it's detected faces in. So we just want to know, well, how many are there in that particular array? So if that number is 0, we've not found any faces. If it's 1, we've found a face. If it's 2, we found 2 faces, and so on. So if the length of faces is greater than 0, then make our lights go green. That means we've detected a face. Otherwise, make them blue. We haven't detected a face. And then we're just going to return that faces array as well as the image, which was the original color image at 320 by 200 pixels. I then created one last function which will write out, using that faces and image and a file name, it will go through for x, y, width and height in faces, draw a rectangle on top of that image. So CV2 rectangle will draw that bounding box over our particular image at the x and y coordinates that are in that faces array. For each face is detected, and then we say what color we want that to be as well, and what the stroke size is as well. The 4 is the stroke size of the rectangle. So RG, but no B. So what's that? Is that a green color, I think? Not sure. And then we do CV2 image write with the file name that we're going to pass in and the image that we've calculated. Okay, so then the last bit of thing there says while true or keyboard interrupt. I've always started to add this keyboard interrupt thing because if you press Control-C, it means you can exit out a bit more gracefully. And then we say faces and image equal detect faces. And if we have that write files enabled by just removing that comment, then it will write out a file. So let's actually change that code so it does write out a file, and it'll write it out every single time it's doing the task. And then we're going to run the code. So let me get over to this view over here, and let me just reposition things a bit so we can see what's going on. Actually, I'll leave that there, and I'm going to run the code, and we should see the output from that. So it'll start saying found faces and so on. Oh, what have I done wrong there? So I did tweak this code before, so there's probably a little bug I just need to fix. file name. There's a typo in the file name. That's the problem. So let me just go back up to there. That looks correct. Yep, and it's just where I passed in just on here. Let's go back to there. So that's just got a typo there I've just done. That should be A and that should be E. Like so. Let's try that again. Just click run on there. Let's go back over to here. Right. Okay, so it's saying found face 0. So I found if I just lean back slightly in my chair, so there's a bit of distance, it's now detected my face. Now I can hide my face. I can show my face. I can hide it and show it. Alex, if you want to come over a second and stand behind me, it'll be able to detect your face and you'll see that it's got 2 faces. I think actually it could see, because it's quite a wide angle of camera this, so if you come behind me there, you can see now it's saying 2 faces, 2 faces, 1 face, 2 face. If I stay still there you go. Are you over there yet? There you go. So Alex is showing your face there. 2 faces found. There we go. So we could actually have a different colour display if it finds more than 1 face, as an example. You can see there the speed that this is running at, so it's not particularly fast. We're not talking Jetson nano speed of detection. We're talking about 1 frame every 1.5 seconds, something like that. We probably could do a few things to optimize the code so it runs a bit faster. However, let's have a look now and see the results. This is going to be a really flattering picture of me and my stomach there, so let me just get this angle here, get it to detect my face, and then click on that. We can see there it's detecting my face. It's put like a nice purple thing in the background. If I just aim this up like so, we can get it to detect my face like that. There we go. And we've got the little bounding box around it as well. There we go. So Adam is saying Harvey Dent AK2 face found. Not sure that's quite right. Oh, there's 2 faces. It's quite a wide angle camera, so it can actually detect when Alex was stood at the back of the room over there. It can actually, if I point it over there actually, it'll probably be able to detect Alex's face from there, if that wire's not in the way. There we go. Your face showing there. Let's see if it detects. Yep, it's detected Alex's face there. How cool is that? And it'll keep overwriting that file every single time it runs. So we can go back to our original running code up there, and we can just do Control. Oops, not that one. That one there, and we can just do Control C in the terminal, and we get keyboard interrupt. Cool. So what do you think about that? How cool is that? We can do all kinds of things with our Raspberry Pi and Python and OpenCV to detect faces. What I want to do next is detect smiles and frowns. Now there are actually some libraries to do that. We could probably get away with trying that right now. So let me just open up the folder. So we've got that default frontal face default library. If I go into SMARS lab, I think I have in the non-SMARS lab, it'd be under the library. We've got the full OpenCV downloaded. Maybe we need to download that. Maybe it's under Deep Learn. Let's go back to the command line and download what we need. So if we go to, I'm just going to jump out just a second to find it on the web, what the actual name of the GitHub repository that's got OpenCV in it. I think it is just OpenCV. And then I shall load that up and we can play around with some different ones. Yeah, I think it's just OpenCV-Python, that's the one. OpenCV-Python. Right, let's go back to our Raspberry Pi and let's get that up there, that view. There we go. So if I do git clone https and then github.com/opencv/opencv-python, I think that's correct. It should grab the entire thing. Now there are quite a few libraries in there for it to download, but I've hardwired this in. You can see on my Trilobot, if I go to that overhead view, I've actually got a cable plugged in there to the network port, just so that this is running as fast as it can. And ask me about these modules as well later. I've got a few cool extra modules that we can play with. Okay, let's go back to the Raspberry Pi. There we go. Okay, so we're going to go into that folder that we've just downloaded. So go to OpenCV Python. Let's have a look in there. And I think it's the CV, is it tests or CV2? It's probably easier to look with the Explorer window. So let's go for that. OpenCV. Let's have a look in the CV2 folder. It's not that one. Where are the files that I am looking for? They're not in there. That's a bit frustrating. Where do they exist? Is it the contrib? No, I just copied it out before, so it must be on this machine. Let me just have a look in SMARS Lab, non-SMARS Lab. So, yes, there's lots of heavy rain going on at the moment in the robot lab, so you might be able to hear that right. I think this is what I was looking for, is it? Nope. I'll not spend much longer if I don't find the thing I'm looking for. I thought I had more of the libraries installed on here, but not to worry if I don't. Okay, no, I can't find them. One last little look to see if it's in there. So I'm looking in the virtual environment that I set up, but actually it might not be in there. It might be in another folder. Okay, not to worry then in that case. Well, that's probably a video for another time. So I'll just look and see if we had that other model, we could grab that file and try and detect faces, as well as faces, smiles and frowns and things like that. Really all it's doing is just more feature detection. So we would run just a different model and it would just detect the features in a different way. And we wouldn't really have to change much of our code. It would still run, but instead of detecting faces, it would actually be just detecting those features instead. Cool, cool. So there's a couple of other things I wanted to cover off in today's video, just while I've got all your attention, because there's some really cool things going on in the background with the channel. So you might notice there's quite a few Pimoroni things going on here. We've got quite a few extra little modules to put in our Trilobot. So one of these is the CO2 sensor. I've got one of the breakout gardens for that. We have a 4-in-1 air quality sensor, so that can measure all kinds of things. We're going to plug that in as well. We also have a bunch of OLEDs, so we can get little screens working on this. I think I do have the gyroscope module as well, which is this tiny little one here as well. So that's the ICM 2948. And a really cool one I can't wait to get playing with. I've not had time to look at it yet. This is a thermal camera. So this is a wide angle thermal camera, and I think it takes about a frame every second or so, but it's thermal, so it can see heat. So we can have that on the very front of our Trilobot, and we can detect things other than just regular images and faces and frowns and all that. We can also detect danger and heat and so on. And so I visited Pimoroni at their office last week, and they managed to provide me with the official battery for the Trilobot. So they'll be supplying these shortly. I think they ordered a bunch of them, but they're just taking a little bit longer to come there. So I've been using this great big battery on my Trilobot, and now I've got the correct size that they have on all their documentation. So if I just go back to our overhead, you can see the difference in size there. The battery I've been using is quite hefty. Maybe if I do it like you can see that a bit better. The battery I've been using is quite hefty compared to this much smaller one. Now the other really cool thing is I took my Trilobot along, and Chris signed the bottom of my Trilobot. So I've got the person who created the Trilobot actually signed my Trilobot. And yeah, got to see some really cool things in their office that they are working on too, and the whole factory, the whole thing. So might be working a bit closer with them in the future on some other content. So that'd be really cool. And yes, I did get a bunch of things as well, such as the new weather hat as well. So I'll be able to look at that. Be a great time to put the weather hat up, but it's a bit extreme weather at the moment. So I'm looking to do a comparison between the WeatherBot and the Enviro hat that you can get from, I think this is like the official Raspberry Pi one, and then this is their take on it, which has probably got a few more extras than this has. So yes, looking forward to doing those videos. Whole bunch of things to get very excited about. I also managed to snag myself I think this is some Pi Hut actually, Raspberry Pi 4 2 gig. It's not even unboxed yet. I've got another camera module so we can do a bit more camera related stuff, and the reason I've got that is because I've also got the compute module. So the compute module, unlike the regular Raspberry Pi, has 2 camera. You can see on the bottom here they've got 2 camera modules. So we'll be able, I've not even opened this yet, we'll be able to have a look at that, and I can't wait to have a play with this bad boy, the Cascade, which is a Raspberry Pi powered retro games computer. So very, very exciting. This is the sort of newer version with the 10-inch screen, USB, it says new for 2020, and it runs Pico 8 as well. So very, very excited about that. And yes, I didn't realise Pimoroni, they create loads of screens. I've got quite a few of their screens already. Let's grab this from over here. I was rifling through my desk before and realised there's another Raspberry Pi. Look at the bad soldering on that. There's another Raspberry Pi that I hadn't actually found to add to my Pi collection, because I'm putting together a cluster at the moment, a Raspberry Pi Zero cluster, and I have another Raspberry Pi Zero on here. I think this is the Zero. Just have to very carefully prise this off without damaging the screen. So yes, this is a Zero. It's not a 2, it's the Wi-Fi version. If I can get that to just focus on there for a second, you can see it's got the shiny little metal thing just there, and that's the Wi-Fi and Bluetooth. And yeah, they make the Hyperpixel, so that's another one of their displays. That's the round Hyperpixel display. I bought this quite a while ago. So Adam's saying, can't wait to see the Cascade. Me too. So looking forward to putting this round display as well on some kind of project. That'll be quite cool, and it's designed to perfectly fit the Zero inside, so we can create some 3D printed container. Awesome. So Adam says he's 3 hours from Land's End, so you're probably getting the brunt of the storm at the moment. So we've had to hunker down in the robot lab. We have other things around the robot lab that can damage it. So the Twitcher Pi bird table that I'd actually set up last week, I've had to take that down because it's very close to the glass and it could smash if we're not careful. The other cool thing is I always try and get into the Raspberry Pi, the official Raspberry Pi magazine, and again we've done it this week, this month, so you can see just there, that's my little Retro Pi. I don't think you can read the text there because the light's too bright, but you can probably just about make out my name there. And yes, that's the Clustered Pi project. Just get a bit of a mention there as well. Cool. So yes, I think that's everything for people who are watching on the replay video. So we'll say goodbye to people who are watching on YouTube on the replay, but people who are watching live, we can have a bit of a Q&A chat from this point forward as well. So let me have a look and see what people have been talking about on the chat.